All right. Thanks everybody for tuning in. This is great. This is a lecture that I've done a couple of times to undergraduate students. And so it's a general overview of the issue, and the audience is for people who are non-majors, not necessarily biology majors, so a general audience, and maybe even new to science. Some of the students were new to science, some of them are not going to go into science. So it's sort of a general talk about the issue for a general audience. So let's see if I can make this work. Nope. So here's an outline of the talk. I'm going to start with the history of road salt use, talk a little bit about how it was discovered, when and how it was discovered in fresh water. I'll talk a bit about how it behaves in the environment with some specifics about groundwater. There are many co-occurring issues. I'm going to talk a little bit about the connection between road salt and lead in the environment. And then I'll finish up talking about some of the best management practices that we have available to us and the next steps we can take to make change happen. So the history of road salt. Road salt started being used in the United States around 1940. In 1940, the USGS reported that 150,000 metric tons of salt were used. And that's in the whole United States. So remember that number, 150,000 metric tons. There is some evidence that road salt was being used before that. But the USGS started recording the amounts in 1940. So it was in the late 60s, early 70s that it was discovered in our fresh water. This is a paper from the journal Science. For those of you who are new to science, this journal is a very prestigious journal. In order to get something published in it, it has to be a pretty important issue. So this is from a study that was done on Irondequoit Bay, where they found that in the winter of 1969 to 70, the quantity and salinity of the dense runoff that accumulated on the bottom of the bay was sufficient to prevent complete vertical mixing of the bay during the spring. So not only did they find salt in the water, but they found enough to affect the function of that body of water. This is from another study published in 1972 in the journal Science, and this is one in which they looked at groundwater contamination in east central Massachusetts, and they reported that the average steady state contamination of groundwater by road salt in the suburban area around Boston would be about 160 milligrams per liter of sodium chloride. That's 100 milligrams of chloride per liter. And that was based on the assumption that the current rates would continue, the current rates of road salt deposition would continue at the current rate. Okay. So what do we know about the natural concentrations of sodium and chloride in the environment? This is a little publication that was done in 1975 in which they looked at the chloride concentration in groundwater in the state of New Hampshire. And they looked at two different time periods. This is from, I can't remember. Oh, I know. This is from the, so I'm playing with my cursor to make it a pointer. From the 1968, I went too far. Oops. Okay, so this is from the 1918 to 1924 time period. And what they found was that the concentrations in the groundwater in New Hampshire ranged from 0.4 to 4.1 milligrams per liter. So this is pre-salting days. So now I'll go to this one. So then they did it again in 1968 to 1970. So this is after salting was started. And in this time period, the concentrations in the groundwater in New Hampshire ranged from 1 to 150 milligrams per liter. And they attributed 83% of this salt in the groundwater to de-icing salt. So what has happened since the 1970s? So this is a graph that shows the total amount of salt used for de-icing in the United States for each year from 1975, if I could do this, through 2017. And there's two things to note. First of all, in the 1970s, the total amount was just about 10 million metric tons. And remember that term from 1940, 150,000 metric tons. So that would have been down around zero. Since the 1970s, there's been a steady increase in the total amount of salt used, and it's more just about doubled since then to about between 20 and 30 and sometimes more than 30 million metric tons of salt. So we're using a lot of salt. So I'm going to show you a series of graphs that are from a publication that was done in 2013 by Castanelli and Robbins, in which they used groundwater sample concentrations from groundwater samples that were collected as part of the Connecticut State Board of Health. And they have data starting in 1894 and going onward. And the concentrations are represented by different colors. So the green color represents background concentration 0 to 2.5. The green gets lighter and lighter until it's yellow, which represents a concentration of 25 to 50 milligrams per liter of chloride. And then as it goes to red, the concentrations increase to 250 to maximum. Okay, so what do we see? So this is a graph, a map showing the groundwater concentrations in Connecticut in 1894, and you can see they're basically background concentrations. And this is in 1902, again, still background concentrations. By 1920 to 1938, the concentrations in groundwater have increased, and there looks to be some developing hot spots. And this is the evidence that we have. This is one of the pieces of evidence that we have that suggests that salt was used before 1940. By 1950 to 1969, you can see that there's less of the green color, more of the lighter green and yellow color, and there's some developing hot spots where the concentrations are relatively high. 1977 to 1978, again, an increase in the spatial area of higher concentrations and some more hot spots. By 1992 to 2005, pretty much there's there's very few places in the state where there are what we would call background concentrations. And then by 2002 to 2007, there's virtually nowhere where the groundwater isn't contaminated by salt. A lot of increasing salt concentrations in the groundwater in the state of Connecticut. So what do we know about what's happening in our own backyard? Since 1986 at Cary Institute, we've been collecting stream water samples from the stream that runs through the property. It's called Wappinger Creek. And so this is a plot of the annual average concentrations of sodium and chloride in the stream. And you see that we see an increase, a steady increase over time in the concentrations. Now, when we first looked at this, it was a bit confusing because the watershed that feeds this stream is nearly all forested. And there hasn't been an increase in the number of roads, the total lane miles of roads or pavement. So essentially there hasn't been an increase in the amount of salt that's used every year. So what could be causing the steady increase in concentration? To get at that answer to that question, we calculated a budget for salt for the watershed where we tallied up all the different sources of salt to the watershed, including road salt and parking area salt, but also including sewage and water softeners and wet deposition and natural sources. And what we discovered, unsurprisingly, is that 90% of the salt input to the stream is from road salt. So we can take that graph, that pie chart, and plot it for each individual year for the record that we have data for. And so that's what this is. This is essentially that pie chart for each individual year. And there's a couple things to note here. First of all, the sort of purplish color represents road salt. So again, the majority of the salt entering that stream is road salt. And then there's this term, and then one of the other things to note is that there isn't an increasing trend in the total amount of salt, road salt, that's being input to the stream. But there's this interesting term, this export minus input. Because we know how much salt is in the stream and moving out of the watershed via the stream, we could calculate the total amount that's put into the stream and subtract that from the amount that leaves via the stream. And so what this shows us is that that number is negative in the early part of the record, which means that there was more input than exported from the watershed. And that means that some of that salt that entered during that period, that entered the watershed, was retained in the watershed. In the latter part of the period, that number is positive. So that means there was more exported than was put into the stream. And so what we think happens is some of that salt that was input in the early part of the data record was exported from the watershed in the latter part of the record. And that is what has caused that steady increase in salt concentration in the stream. Because we have all this information, we have all this data on the total amount of salt that is coming into the watershed. We know how much water is coming into the watershed, into the stream. We know we can estimate the amount of water that's stored in the groundwater. We wrote this mass balance model, very simple model, in which we started using road salt in 1956 and just used the same amount every year. And what the model shows us is that, in fact, we see, as we see in our stream, we see a steady increase in concentration, and then the concentration levels out more or less. And then what we did was to see what would happen in the future, to predict what would happen in the future. We said, we're going to decrease the amount of salt that we use by 18.5%, which is the amount that we can achieve with the current best management practices. And so what you can see is that over time, the concentration declines and then it levels off. But what's really important is that the time that it takes to achieve that level concentration is a couple of decades. And so that is what we refer to as the legacy effect. It takes a couple decades for all that salt that's accumulated in the watershed to be flushed out. So one of the things we did just as an exercise was we said, what if we decrease the amount of salt we use to zero? We're not suggesting that that happen, that we try to do that, but we just did this to see what would happen if we do that. And what you see is that, in fact, the concentrations decline to basically background levels. But again, it takes a couple of decades for that to happen. So that is illustrating what we call the legacy effect. One of the things you might notice in this graph is when we plot the actual stream concentration, we see that in the latter part of this period, we have some pretty extremely high concentrations and some low concentrations, and there's some crazy swings back and forth. So what could be causing that? And we think that this might have to do with the volume of water in the stream. Why do we think that? So This is a plot that sort of explains that. It is the daily average concentration over each day is each one of these days on this graph represents an average of about 13 years. And this is a plot with Julian day on the x-axis, and Julian day is the day of the year. So Julian day 1 is January 1st, Julian day 365 is December 31st, Julian day 90 is about April 1st, and 270 is sometime in October. So this graph shows the stream height, which is in blue, and the conductivity in red. So they're plotted together for each day of the year. And I want you to focus just on this part right here, which represents the late spring to autumn. And what you can see is that as the stream level declines, the conductivity increases. And the conductivity is a representation of the total concentration of ions in the water, including chloride ion. So we think that what we see in that graph with the wild swings from year to year in concentration is possibly due to differences in the level of water in the stream in those years. So I'm going to switch directions a little bit. I talked about how the salt behaves in stream water. And so now I'm going to focus on how it behaves in groundwater. And I'm going to use this study that we published in 2018. That was a GIS analysis from a township in southeastern New York called East Fishkill. And East Fishkill has a law on its books that says every time a property changes hands, is bought and sold and bought, a sample needs to be taken of that drinking water well, and the sample analyzed and the data made public. So this provided us with a really rich set of a data set of about 1,000 samples to use for a GIS analysis. What did we find? Well, one of the obvious questions to ask was, does it matter if wells are adjacent to major versus minor roads? And so in this graph, you'll see sodium on the left and chloride on the right. Minor roads are represented by the orange bars, and major roads are represented by the blue bars. So this is a median concentration of sodium and chloride for wells that were adjacent to minor and major roads. And we found no significant difference between minor wells, the chloride concentration in wells adjacent to minor versus major roads. And I'll point out that while we found no significant difference, other studies have found that the concentrations of salt in groundwater adjacent to major roads are significantly higher than in groundwater adjacent to minor roads. All right. What we did find that was important was that these two metrics have made a difference. So distance to the nearest road and the percent impervious surface cover. So what we found was that as you go farther and farther from the nearest road, as the distance between the well and the nearest road increases, the concentration of salt in those wells decreases. And then conversely, as the percent impervious surface cover around those wells increases, the concentration increases. So the more impervious surface cover around a well, the higher the concentration. The closer to the nearest road the well is, the higher the concentration. So this isn't surprising. We did what's called a hot spot, cold spot analysis, and this is an analysis where we looked for clustering of high concentrations and clustering of low concentrations. And we did find a couple of spots in the township where there are clusters of high concentrations, and then a couple of spots in the town where there are clusters of low concentrations. So the salt is not evenly distributed necessarily. It can be found in these hot spots and within the groundwater in this township. All right, I'm going to switch directions a little bit again. There is increasing concern about the co-contaminants with road salt, specifically with lead. The Flint, Michigan water crisis revealed that the lead concentrations in drinking water increased when the chloride concentrations increased. And that happened because the city switched to using water from the Flint River, which was contaminated with road salt. And so the question that everybody is asking is if this is a widespread phenomenon. So some of you probably have played this game of Clue, and you may remember that one of the murder weapons in the game is a lead pipe. And lead pipes, there was a time when houses had their drinking water flowing through lead pipes, because lead is flexible and they could bend it around corners. That no longer is the case. There are, I won't say there are none, but the lead pipes are not found in houses anymore, but there are lead solder joints, and there's lead in fixtures like faucets in the pipes of houses. So what do we know about the lead and the road salt connection? There are two ways that that road salt can cause the leaching of lead and other heavy metals into groundwater. One is from soil and the other is from pipes. And this is an illustration that was published by Schuler and Relia in 2018. And it's a diagram that illustrates how road salt causes the leaching of heavy metals into groundwater. So I want you to focus just on this diagram on the left where road salt is absent. And this is a cross section of the land surface of a piece of land, and here's the road. And the heavy metal concentration is illustrated by down here. It's on the lower left. It's the dark represents heavy metal concentrations. The light, low heavy metal concentrations. So you see when road salt is absent, some of the heavy metals flow off of the road into the soil, and they pretty much stay in these upper horizons. Very little of it is carried down into the deep groundwater where drinking water wells tap. So now look at this illustration on the right where road salt is present. So some of the heavy metals come off of the road in addition to the road salt. And what happens is now these heavy metals are being leached from these upper horizons. So you see a lower concentration than in the upper horizons than when road salt is absent. And you see that it's being carried down into the lower horizons and the deeper groundwater. And you see heavy metal concentrations now where these drinking water wells are tapped into. So how does that happen? It happens via a mechanism called ion exchange, and this is a diagram that illustrates that. Here you have a soil particle, which has a whole bunch of negative charges along its surface, and it has adhering to those negative charges are some positively charged ions. So this is great. Now what happens is if you add salt, so sodium or calcium or magnesium chloride, to this solution, you get the displacement of this lead ion from the surface of the soil. And then the lead ion now is in solution in the solution of water that's surrounding this soil particle. And that's how it can be carried by gravity down into deeper groundwater. So does this really happen? So this is a study that was done in 1992 where they took tubes of soil they collected it from near a road, and they treated that soil. They poured water into those different tubes. Some of the water was deionized water, and then they had these increasing concentrations of salt. So some of the tubes got 0.01 molar NaCl, some got 0.05, some got 0.1 molar concentrations of sodium chloride. And then they analyzed what came out the bottom of the tube. And what they found was, in fact, as you increase the concentration of salt, you see that lead and other heavy metals are leached out of that soil. So the answer is yes, we do see that happening. So as I said, the other way that salt can affect the leaching of lead and other heavy metals is leaching not through soil, but leaching from the inside of drinking water pipes. So this is from a paper that was published in Environmental Science and Technology in 2018, where they looked at the distribution of salt and lead in groundwater that was associated with this long uncovered salt storage shed. The study took place in the town of Orleans, New York, up on the St. Lawrence Seaway. And what did they find? So I'm going to point out these top two panels of this graph. So here's the salt barn, and you can see that, in fact, the sodium concentration and the chloride concentration in the groundwater around the salt barn is indeed high. But then if you look down here on the bottom right, here's a panel that shows the lead concentration in the groundwater in this area. And you see there is some lead in the groundwater around the salt barn, but by and large, most of the lead they found in this study was very some distance from that salt barn. And if you look back up here, there's very little salt in the groundwater in that portion of the study. So they didn't find an association between lead and salt in the groundwater in this area. But then they asked the question, can lead even be leached from pipes if you have salt in the water? So what they did was they created some simulated lead tin solder joints, and they put them in beakers full of water that had increasing concentrations of chloride, and they let them soak for a couple days, and then they analyzed the lead concentration. And what they found was that, yes, as you increase the concentration of salt, you see more lead leached from these simulated joints, but not at the highest concentration. So there's some indication that we should see lead in drinking water associated with chloride, but we don't see it when we look at it across a geographic area. So the jury is still out on this question, and there is likely some confounding factors that we don't understand yet. All right, so hopefully I have convinced you that road salt is a problem, and we need to address it. We need to take steps to reduce the amount of salt, at least to reduce the amount of salt that we use on a broad scale. So a couple of years ago, the Cary Institute published this report in which we outlined the issue. And then we also listed some steps we can take to mitigate. And these are recommendations that we made. There are some low-hanging fruit, one of which is salt storage facilities. There's a whole range of ways that salt can be stored. It's often stored in these open-faced sheds, which is problematic because the salt can just dissolve and run off into water bodies. So one of the recommendations we make is to change all salt storage facilities so that the salt is completely covered. Some other best management practices that we recommend are computer controls in the trucks that distribute the salt so that the driver can adjust the amount of salt that's coming out of the hopper. Pre-treating roads with salt brine has turned out to be very effective. There was one study published in which they reported that 35% less salt was used overall when the roads were pre-treated with brine. You probably have noticed that in the wintertime before an event starts, that you see these lines of salt on the road. That's pre-treatment with a brine solution. There are plows that are called live edge plows that the edge of the plow blade conforms to the surface of the road, so it removes ice and snow from holes and as well as little mounds on the road surface. Removing more of the ice and snow means that less salt is needed. And then these road weather information systems provide a way for the road crews and the public to look at the conditions of the road itself and decide, do I need to go out there and treat the road, or for the public, should I be out there driving on it? So those are some recommendations for ways to reduce the amount of salt. Another tact that we could take is to beef up our protection of our drinking water. Our drinking water is protected by the Safe Drinking Water Act. It has primary, secondary, and secondary standards, and then this contaminant candidate list. The primary standards are enforced standards. The public drinking water supplies can't go over the concentrations of those chemicals that are listed as primary standards. There are secondary standards. These are non-enforceable guidelines. Chloride fits in that category, and the recommendation by the Safe Drinking Water Act is 250 milligrams per liter by the EPA, who administers the Safe Drinking Water Act. 250 milligrams per liter. And then sodium is on this contaminant candidate list, which means that it's under review. It has been for probably about 15 years. The recommended limit for sodium is 220 milligrams per liter. Some states require public notification if sodium exceeds 20 milligrams per liter in the public drinking water supply. So one of our suggestions was that we shift sodium from that contaminant candidate list, make it a primary standard. It's important to note that the Safe Drinking Water Act covers only public drinking water supplies, not private drinking water wells. And in East Fishkill, we found that half the wells that were sampled had sodium concentration that exceeded 20 milligrams per liter. So one of our recommendations is that that private drinking water wells be tested regularly for a suite of contaminants, including sodium chloride and lead. We recognize that there are some impediments to implementing these best management practices. So we identify those and we make some suggestions for how to address them. First of all, a lot of municipalities can't afford the upfront cost of new equipment. So we suggest the possibility of consolidating services with other municipalities or with different levels of government. Private contractors are a big black box. We really don't know what they're doing. They, in fact, have a disincentive to reduce the amount of salt they use. There are some states that offer liability relief to private contractors who go through best management practice training. Some companies and organizations, colleges, or companies like Target and Walmart have sustainability plans. We suggest that they include their salt use in their sustainability plans. And probably most important is convincing private contractors to adequately store their salt so that there isn't contamination from a point source. Some municipalities out in the Western United States surveyed the public to find out what whether the public even expects or wants all of their roads to be 100% ice-free 100% of the time. And they were surprised to discover that there are some roads that people are okay with snow and ice on. So one of the suggestions we make is to do that, to survey the public and engage the policymakers in this process, to find out if there are some roads we can leave completely unsalted or with a reduction in salt use. And then of utmost importance is continuing to do research. There's this organization called clearroads.org, sort of the clearinghouse of best management practices and what we know about how they work. It's incredibly surprising that we don't necessarily have data from municipalities or private contractors. So we suggest that we ensure that we build that data collection into management plans. So some takeaways. I hope you feel like I do, that we can balance environmental stewardship with safety and fiscal responsibility. Because of that legacy effect, the time to act is now. And the way to do that is to create a culture of change. So I'll leave you with this, one of my favorite quotes: never doubt that a small group of thoughtful, committed citizens can change the world, by Margaret Mead. So with that, thanks for your attention. I'm happy to take some questions. You can either put them in the chat box or you can unmute yourself and shout out. But thanks for your attention. Questions? Nobody? Chris Solomon says, great talk, Vicky. Thanks. Thank you, Chris.
Hey, Vicky, this is Gary. Can you hear me?
Hi, Gary. Yeah.
I was wondering, you were talking about you didn't see any significant difference between wells in East Fishkill that were close to major roads versus minor roads. And I was wondering what's the difference in salt application rate per mile for the minor roads and the major roads, because they might be salted by different entities, for the county or the town.
Yeah, that's right. So the major roads were all state roads. The minor roads were either county or town roads. I don't know specifically for the town of East Fishkill how this shakes out. When we did our study back early on, when I have kept track of the salt use in the watershed that feeds the Wappinger Creek, and what I have discovered is that the total amount of salt used by both entities, state and town, is the same, and county is the same. The state has access to fancier equipment, so it may look like they're using more salt, but they're actually using less. They're just doing it more often. Whereas the towns and the counties are distributing, a lot more rock salt, and they're less efficient. So the total amount, I think, is the same. But I don't know exactly for East Fishkill. Sarah asks, I may have missed this, but where would the lead be coming from that could be leached with road salt? There's a lot of lead that is just on roadways that has come off of cars over time. So that's where it would be coming from, next to roads, adjacent to roads. We actually have some lead in our drinking water. Lead was only banned as a part of solder that is used to connect copper pipes. The lead in solder was banned in 1986. So if you have a house, which I know you do, have a house that was built before 1986, it likely has lead in the solder joints. But even if you have a house built after 1986, there is likely to be some lead in the brass that is part of your fixtures, your faucets in your house. A lot of good talks. I don't see any more questions. Oh, thanks, Vicky. Yeah, so thank you guys all for, this is great. 32 people signed in to listen to this. I hope it wasn't too much of a big overview, but looks like some people got something out of it. So you're welcome. Right. I don't see or hear anymore. I guess I should stop recording. Okay, so thank you guys, everybody. Everybody, please stay well. And have a great afternoon. Can the recording be made available to the public? Gosh, I guess so. That's a question for Lori and Matt and all those guys. All right. Thanks, everybody.